Hello all, I hope you are doing well. So today we are going to discuss quantum confinement. In quantum mechanics, all of you must have studied this topic, which is called particle in a box model. So let us revise this topic in a short way. So if you remember that this is a particle, this black stuff here, and which is confined in a potential well, and this particle is confined to move in a very narrow dimension or through a very narrow length. Suppose this length in which the particle is allowed to move is having the length is L, suppose, and then by quantum mechanical derivations we learned that the energy value of such a confined particle En is having an expression like this, which is n square divided by 8 ml square. So h is Planck's constant, m is the mass of the particle, and L, capital L, is the length of this confined dimension, and n is an integer. Therefore, what we can understand from this particle in a box model, that the energy values of a particle confined to move along a given direction is quantized. It doesn't have continuous values of energy. So next, so here a comparison has been done between the energies possessed by a free particle and confined particles. So for a free particle, the energy value E is equal to h cat square k square by twice m. Therefore, this energy value for a free particle is having the shape of a parabola. And here on the right side, this is a joint plot of energy values of a confined particle and a free particle. Confined particle, this free particle is having an energy which is represented by this parabola, and the confined particle has energies which are represented by E1, E2, E3 and E4. So you can see that as opposed to the continuous values of energy for the free particle, the confined particle is having only fixed values of energy like E1, E2, E3 and E4. There cannot be any energy value which can be possessed by the confined particle and having a value between E3 and E4. Similarly, between E2 and E3, this particle cannot have any values, and also between E1 and E2, there cannot be any energy values possessed by the confined particle. So let us understand this table first. So in this table we have shown various dimensions, 3 dimensions to 0 dimensions. So 3 dimension, let us call this a bulk structure. Then in 2 dimensions, let us call this structure as a quantum well, and in 1 dimension let us call this structure a quantum wire, and in 0 dimension let us call this structure as a quantum dot. Now you might be thinking why we have to use the word quantum when we are discussing the behavior of nanomaterials or nanoparticles. So this word quantum is coming into picture. So these particles are very microscopic. I mean, nanoscale materials are very small sized particles, and therefore classical physics is not adequate to describe their properties. Classical physics is adequate to describe properties of bulk or macroscopic particles, but for microscopic or nanoscopic materials whose properties are mainly due to the surface atoms and the electrons influencing the properties of surface atoms, in that case their physical properties can be well described by the quantum mechanical principles, and that is why we have to use the term quantum confinement, or we have to understand this concept of quantum confinement to understand physical properties of nanoscopic materials. So for a bulk dimension, you see this blue particle is a bulk particle. It's a large sized particle, so it has confinement dimension of 0 and free dimension of 3. So what do we understand by this? That means a charge carrier is able to move in all three directions in a bulk material. Three directions means if we consider x axis, y axis, z axis, those three can be considered as free dimensions. That means and a charge carrier is not confined along any direction. So it is able to move in all three axes or directions. So then this red structure, which we called as quantum well. So a quantum well has a confinement of one dimension, and it has two free dimensions. So of course all these figures are not to scale, this is just for your understanding. So you see along this height a charge carrier is confined to move. I mean, the charge carrier will feel the boundaries of this structure if it is allowed to move along this height of this object. But this charge carrier is free to move from this direction to this direction, and from this direction to this direction. I mean, along breadth and length the charge carrier can move. So if a charge carrier is restricted to move along one direction, but it is free to move along two other directions, in such cases we call the structure as quantum wells. So quantum wells have one confinement direction and two free dimensions. So now let us look at this green structure. Such structures are called as quantum wires. So in quantum wires the confinement dimension is 2, but the free dimension is 1. So here you can see along this height and along this breadth the particle is confined to move, but along this length the particle is free to move. I mean, this is a macroscopic dimension, whereas these two, this length and breadth, are microscopic or nanoscopic dimensions. Therefore the particle is confined to move along two dimensions, so it has two confinement dimensions, and at the same time it has one free dimension. So such structures are called quantum wires. So now another type of confinement can be found in this structure called quantum dots. So we have this yellow structure is called quantum dots. So they are called zero dimensional structure. Zero dimensional means they have zero free dimension. That means the charge carrier is not allowed to move along any direction. Suppose this charge carrier, which may be either an electron or a hole, it cannot move along any direction. It is confined to move along this length, this breadth, or even the this is the height, this is the breadth, and this is the length. So this charge carrier is confined to move along length, breadth, and height. And if we consider the structure to be a cubic structure, so in other words, the particle experiences three-dimensional confinement, and therefore it has zero free dimensions. So I hope this table and this figure is clear to you. So in short, in three-dimensional material there is no bulk materials, so there is no confinement dimension, but there are three free dimensions. And similarly, if we reduce the size of this material to that of a quantum dot, so in that case we get three confinement dimensions and zero free dimensions. So I think this is enough for this video, and in the next video we are going to learn about excitons and a bit more about quantum confinement. Thank you.